Okay, so hopefully this will, and try to talk extra loud so that the microphone back up. Okay, that's good. Yeah, so again, midterm, almost all done, not all done, so we won't go over it today. We will cover it on Wednesday. And today we're going to go finish up this set of notes right here. And there's a new set of notes in the topic 6 folder that we may or may not get to. Again, there's a handout printed version of this set of notes up front. So we're in chapter 4 right here on overfitting. We talked about 4.1, not directly, but all the material of 4.1 we covered implicitly while we were talking about other sections of the course. And the last time we started talking about section 4.2 here, regularization. Regularization, the big picture idea about the why we care about regularization is that it is another tool for us to prevent overfitting. So regularization, another tool to prevent overfitting. So similar to how we have the tool of adjusting the VC dimension, we'll have this other regularization we will now to prevent overfitting or prevent underfitting as well. The last time we talked about this soft order constraint, the big picture idea of the soft order constraint is that when we have this subject to over here, this is like a constraint inside of our hypothesis class. And so if we had our perceptron hypothesis class, then the previous version, I'll write in blue, sign X transpose W, where W is contained in R to the D. And now this new version that contains this subject to right here adds an additional constraint of this omega function, which is different than the omega from asymptotic notation. It's just the random or an arbitrary name of a Greek letter function that the author chose to use here. Not a commonly used one in particular, but one that they chose to use, omega right here, omega of W. And again, there's this one-to-one correspondence between hypothesis classes and weights inside of our hypothesis class. And so the textbook and I and many other sources will go back and forth between the H and the W here. Pictographically, what this constraint here does is that by default, the perceptron hypothesis class, as we have previously been talking about it, these are the W1, W2, this is the weight space that we're looking at. In the past, our weight space has not been constrained to any particular location in the hypercube, or so hyper meaning the just higher dimension, hypercube in the space here, R to the D, visualized here in 2 dimensions, so a plane. We've not constrained ourselves to anywhere in the plane. But this constraint over here, this omega of W, sorry, I forgot to keep writing, less than or equal to C, is adding some constraint onto where we're allowed to be inside of this space. And the most common one of these omega functions is the L2 normalization, which looks like a circle. Now we're allowed to be anywhere inside of this circle if our omega equals L2. Another possibility of this omega function, I have 3 common ones listed down here, the L1, L2, and elastic net regularizer. The L2 regularizer, again, is it's called L2 because it's based on the L2 norm over here. The L1 norm, though, is looks like a diamond shape. So draw this to match up. This circle is intended to be actually a circle, though, centered around the origin with a constant radius everywhere. So this diamond shape is actually like a square turned on its side right here. And then the elastic net, this one in orange, that's the omega is the L1. And the elastic net is like an interpolation between the L2 and the L1 regularizer here. It allows us to, or the only difference between elastic net and L1 and L2 is that it's the sum of weighted sum between L1 and L2. allowing us to say how much we want in each of those two regularizers. We'll see here in a little bit that they have different properties, and so might make sense to pick some of those properties from one, but not from the other. This is about where we left off last time, so this should all be review of the stuff that we talked about last time. One of the things that I said at a high level is that there will be many different versions of regularization that we'll talk about that will all be equivalent. And so this one is useful for visualizing how a subset relationship can exist between certain hypothesis classes. That if we have a very small C value, if our radius over here is very small, then that's definitely a subset. This small circle right here is definitely a subset of this larger circle. And we've talked about a lot in detail about how these subset relationships affect our in-sample and out-of-sample errors. It turns out, though, that this type of optimization where we have a constraint over here, this is called constrained optimization, when we have the subject to this thing that I have underlined, also called a constraint. And so this is a constrained optimization problem. The SGD, 1 SGD, 2 SGD, 1 GD, 2 GD stuff that we talked about in the past does not work directly on these constrained optimization problems. And so this is useful statistically, but it's not super useful computationally. The next page will go on to an equivalent version of regularization that'll be give us a little bit more insight into the statistics of what's going on, but it's really going to be more useful from a computational perspective. So this definition 2 right here about the augmented error is our second equivalent definition of regularization. And here in augmented error, this line 3 right here is our new optimization problem where we are no longer optimizing E in directly. This E aug is what we are optimizing, and E aug is the sum of E in plus lambda times this omega H. This omega right here, this is the same omega from the previous page. But this lambda is not something that was on the previous page, so this is something new to us. And there's this theorem right here, which the textbook states very, very informally, but it's that if lambda is set to 1 over c, asymptotically theta of 1 over c, then under reasonable conditions, which everything that we care about satisfies, optimizing this augmented error is equivalent to optimizing the soft order constraint that we had above. The only difference is that lambda is the inverse of c. Lambda is 1 over c. So it will often be the case that we will talk about regularization in this format right here, but it will always be the case that we will optimize the regularized problem in this format right here. Because this is what we know how to do. We know how to optimize just a single function without any constraints being applied to it. This fact 1 here is gives us some statistical intuition about why this augmented error might be useful. So if we are somehow able to set our omega function to the generalization error, then it turns out that our augmented error would be equal to En plus En minus E out, which would be about equal to E out. Make that a little bit more obvious. Let's change the signs over here so that it's a negative En and a positive E out, so that the Ens are essentially canceling out, and we're left with just the E out over here. So the textbook occasionally talks about this omega function right here as somehow representing the complexity of our model. Omega controls the complexity. . And this is one way of thinking about regularization, as if you somehow were able to find a regularization function that really did capture your generalization error, then we would be optimizing directly the out of sample error with a function like this. In practice, turns out that we don't have any real reason to think that these L1, L2 elastic net regularizers are exactly representative of our generalization error. So this is just a sort of a hopeful statement. It's not something that is ever guaranteed to be true in any way. But if it were true, then our augmented error would be our out of sample error, and we'd be optimizing that directly. Any questions so far? Yes.
So if you optimize G in definition 1 and optimize G in definition 2, or is it the same?
So the question is, in definition 2 and definition 1, we have two different versions, two different definitions of this G function. And are these the same? And the answer is that as long as your lambda right here is and C values are set appropriately, then they are in fact the same. So these are fully equivalent definitions of regularization, and we will see, we will have to be able to go back and forth between these two. Some of the libraries that we'll be using in your next program assignments, we'll be talking about lambda here for the regularization term. Some of them will be talking about the C term up here, and you'll have to be able to go back and forth about understanding just that C is 1 over lambda, or lambda is 1 over C.
You for like the L1 and L2 norms in the subsets, and you drew a diamond in the circle, you drew, you were showing that subset of the plot of the L. If it was like a small diamond, would that be a subset of like a bigger circle? Or it'd be the same?
Yeah, that's a good question here. So the question is that the way that I have drawn this, the this inner circle right here, say with a very small arc radius, we'll call this inner radius 1 right here, and this outer radius, say 10. This inner radius has it fits inside of the square right here for the L1 regularizer. And so the question is there ever a situation where if we set our C value small enough, the C again is the radius of these circles. If we set our C value small enough, will the, say, L1 regularizer be a subset of L2, or L2 be a subset of L1? And the answer is that in high dimensional spaces, they will never be subsets of each other. It only happens to be the case in low dimensional spaces that this happens. In high dimensional spaces, you have to change the inner radius to be so small that it's never useful to think about these different regularizers as being subsets of each other. So the subset relation that we do care about is that for any one particular regularizer, for any particular omega, our hypothesis class on that omega and some particular C value, that will be a subset of the same hypothesis class with the same regularizer and a different C value, C1 and C2 over here, if C1 is less than or equal to C2. But we'll never care about the situation where these omega values are different regularizers. Yeah, good question. Okay, so what we're going to spend the majority of today talking about is the different properties of these L1, L2 elastic net regularizers and how changing this C value up here or this lambda value down here affects our regularization ability, affects our ability to underfit or overfit the data. The first thing that we're going to do is talk about a new hypothesis class in order to do that. So this is a new hypothesis class right here, the hypothesis class of K-sparse half spaces. So it's very similar to the half spaces hypothesis class that we've seen before. except that there's this new constraint right here. New constraint. This is a hypothesis class that's not easy to visualize because if it is happening in multiple dimensions, or this new constraint really only matters in high dimensions, and so it's hard to visualize. But with this constraint right here, it's saying the number of non-zeros of our weight vector here is equal to k. And so we're not learning all dimensions. Not all dimensions will be meaningfully applied of our x data. We're going to ignore many of those dimensions. So the purpose of this class is to ignore many dimensions of the input data. And in particular, all of the dimensions where w is equal to 0 is what we will ignore. All dimensions where w equals 0. And so since w is d-dimensional and k of them are non-zero, that will be d minus k. Dimensions are 0. When we do this multiplication over here, we'll have a 0 times the corresponding dimension in x, and so we will ignore those dimensions. A simple fact that you'll need to know but not prove is that the VC dimension of this hypothesis class is k log d. And so if our hypothesis is very sparse, our hypothesis class is very sparse, our W matrix, our W vector here is very sparse, which means that our number of non-zeros is very small, then k over here will also be very small, and our VC dimension will be much, much lower than the non-sparse case. VC dimension much lower than non-sparse case when k is much less than d. So this is a very useful hypothesis class. The problem with this hypothesis class, though, is that it is non-convex. And so this hypothesis class cannot be optimized directly. Instead, when we are trying to learn something in this hypothesis class, we're going to use the standard half spaces hypothesis class plus L1 regularization. In order to learn in this hypothesis class, use L1 regularization plus standard perceptron hypothesis class, or half spaces hypothesis class. And the key thing about L1 regularization is that L1 regularization induces sparsity. So here again, sparsity, this is a sparse hypothesis class because our number of non-zeros here of W is small. It is not equal to D. And that gives us this better VC dimension over here. So it gives us much more statistical accuracy with our generalization here. And the downside of that is that it's harder to optimize, non-convex, but L1 regularization is a convex operation that turns out to induce this sparsity. I'm going to draw a picture here that's going to illustrate why L1 regularization induces this sparsity. This picture it's a standard picture that everybody is expected to have seen before at about L1 regularization. It's also a picture that is hard to instantly have it click about why what's happening is actually very important here. And it's also a picture that is not going to be something that you'll be required to draw for your final exam. So again, the purpose of this is to help get you some intuition about this L1 regularizer and why it's helpful, but if it doesn't fully click, then that's okay. What I've drawn here is my weight space here, say W1 and W2, and we're going to try to learn a half space that is sparse in one dimension. So we're not considering both W1 and W2 here. We need to somehow pick, do I use just W1 or do I use just W2? And then what is the weight inside of W1 and W2 that I use? In magenta over here, I'm going to draw my actual loss function. So this will be the W star, and then we'll have some sort of convex sets. I'll draw them a little bit diagonal-ish. This, get my hand less cramped so I can draw good circles here because good shapes are going to be important to see what's coming, what's going on. And yeah, so I have 3 convex shapes here. Again, this is my in-sample error as a function of the location in the hypothesis class. And I'm going to draw two different L1 regularized subsets of this hypothesis space. The first one is way out here. So again, the L1 regularizer makes these sort of diamond shapes. It's a rotated hypercube. And we're restricted that our W parameters that we select must be inside of this hypothesis class right here, inside of this diamond. So this W star out here, we in particular cannot select this point exactly because we have to be inside of this diamond shape right here. And so the point here that's going to minimize this this shape right here is this point right here. Inside of this diamond, the point on inside of the W shape that minimizes E sub n is this point right here. All the other points inside of this diamond have a larger in-sample error than this point right here. So this is a non-sparse, at this point right here, that is a non-sparse solution because we're considering both the W1 value and the W2 values at the same time right here. This particular hypothesis depends on both W1 and W2. But if I make my C value smaller, if I make my hypothesis less complex, if I add a constraint, a stronger constraint to my hypothesis class using this subset hypothesis class right here, then at this point, for this particular C value, call this the blue C, and then there's a gray C value, which is even larger. The blue C value is smaller than the gray C value, so it has a stronger regularization. But at this point, this is the optimal hypothesis class, the optimal hypothesis in the hypothesis class that minimizes my in-sample error. At some point, when our hypothesis, when our C values here, our regularization strength shrinks to a small value, this radius shrinks to a small value, then this W2 parameter here is no longer relevant at all for the prediction. We only consider the W1 parameter. And even if we didn't want to consider the W2 parameter, all of the hypotheses in this blue space over here that consider W2, meaning they are off the axis over here, they don't touch this black horizontal line, any one of those hypotheses in this blue space over here have a worse in-sample error than this hypothesis right here. So this this blue solution here is sparse. It's sparse because only W1 contributes to the W vector or to our hypothesis. W2 is in particular equal to 0. Any non-zero value would either take us outside of this constraint right here, or it would make the in-sample error worse. Question, Angie?
Yeah, shouldn't the C1, C2 be actually corresponding to the diagonals instead of like this? The perpendicular lines?
Question is, my C1 and C2 here corresponding to the diagonals. I'm not sure
Like
what you
to
mean.
the vertices, because that's the bound, isn't it?
So your question is here that C2 here I drew as a diagonal like here, and the question is, why didn't I draw it as a straight line coming out to the vertex over here?
Right, because doesn't it have to be less than that?
So the L1 norm is the absolute value of the components. And so all of these points here along this rectangle have the same absolute value of the component. So the this C2 here, I drew it out to this point because the whatever the L1 norm of this point is right here is equal to the L1 norm of this point right here. So we often talk about these as this shape right here. This is like an L1 circle, and this is like a radius of that circle. That this is the line of constant distance with the L1 way of measuring distance. So it's not a standard sort of circle. The standard sort of circle uses the L2 distance as the measure of points, measure of distance between points. But this is an L1 circle right here, so it doesn't really matter where we draw the line to. The key thing here, the key intuition about why the L1 norm induces this sparsity is because it's like a pointy shape over here, and so these convex sets, which are the level sets of my in-sample error, they are the locations of constant in-sample error. They will intersect at the pointy part before they intersect at the line part when we have our regularization sufficiently strong, which means my C value is sufficiently small. One summarization sentence down here is that C going down implies the in Z of W going up. And so if you need your number of non-zeros to go up, if you sorry, I wrote that backwards. The number of zeros goes up, the number of non-zeros goes down. We started off with 2 non-zeros when C was large, and when we made C smaller, we went down to 1 non-zero value. I'll come back for questions in just 1 second. Another important relation, anytime we're talking about how these C values change, it's important to also remember that the lambda value. We will sometimes see people working with lambda, sometimes see people working with C. So as lambda increases, that's equivalent to saying that C is decreasing. And so lambda increasing implies the number of non-zeros will also go down, or the sparsity will increase. The number of zeros goes up. Questions, Frank?
So is regularization always along the axes as the vertices?
L1 regularization always has this square rotated form that is likely to intersect these contour lines along the axis. It's not guaranteed to intersect along the axis because if the regularization is weak, if the constraint is large, then it will intersect either along the diagonal here, or if the constraint is sufficiently large, then so if the constraint is say way out here, then there is no like intersection to happen, because our true optimal is contained within our actual subset down here. So as you're shrink your C value, you're more and more likely to intersect on these points instead of these lines, or actually be contained inside the subset, and you get your number of non-zeros to go down.
But the squares vertices will always be on axis.
For L1 regularization, this is what L1 regularization always looks like, but the other forms of regularization will look different. Like the L2 regularization forms actual circles. Good questions. Other questions so far? Okay, this in note 2 here, this giant table is the summary takeaway, the thing that you have to take away from this section of the textbook. And so we'll go through all of these rows and talk about, sort of fill out this table here, how lambda increasing or C decreasing affects all of these properties of things that I might care about. So first of all is our in-sample error. As C goes down or lambda goes up, regularization gets stronger and stronger. We become a subset of what we used to be. And so the in-sample error here is going to get worse. It's going to go up. C going down implies the in-sample error is going up because we are in this subset relationship. We're going into a subset, so the in-sample error is going to be bigger. But as we add more regularization, the counterbalancing effect of that is that our generalization error will go down. For the VC dimension, we had some sort of proof about this. We could bound the generalization error based on our VC dimension. With our regularization, there is no concrete bounds about our generalization error, and so there is no like target value that we know we should be looking for. It's a much less precise tool that we have. So typically people will first optimize the VC dimension and then go about optimizing these regularization parameters. What we ultimately care about is the out of sample error, but because these two effects are counterbalancing each other, we don't know which one's going to be the results in the best out of sample error, and so we will have to choose that if we are currently underfitting the data, then we will want more regularization. We will want to, if we are underfitting the data, then we will want to increase our C value here. And if we're overfitting the data, we will want to decrease our C value. As we make the C value go down, so this part right here, this is what we talked about last time. With the subset relationship, the stuff we started talking about today with this number of non-zeros of W, as C goes down, as we get more and more constraints on our model, the regularization strength increases. For L1 regularization, that will make our number of non-zero values go down. We'll get more sparse as C goes down. And that's what this picture up here was trying to illustrate. And that's what this our conclusion sentence down here is giving us. The VC dimension will also go down with an asterisk that you can't, the asterisk here is that you have to first decide what you want your VC dimension to be, and then set L1 regularization appropriately in order to use the VC bounds. Decide VC dimension, then set L1 regularization to achieve that VC dimension. And not vice versa. If you use L1 regularization and you get a sparsity of 50%, that doesn't mean that your VC dimension is half of what it was. You have to make that decision in the right order. The time per iteration here, turns out to go, one of the disadvantages of L1 regularization is that it's, very slow. The time per iteration here goes way, way up. Sorry. The time per iteration stays the same. It's the number of iterations that goes way, way up here. The reason for that is that intuitively, things that are more quadratic are easier to optimize. Things that have nicer, rounder shapes, easier to optimize. L2 regularization, all the same effects as L1 regularization for our in-sample error and generalization error. So going up, going down, question mark. As we increase the L2 regularization, we get a subset relationship again. So that makes our in-sample error go up, generalization error go down. How it affects the out-of-sample error depends on which one of these two is the largest. We have no effect on our number of non-zeros, no effect on the VC dimension, no effect on the time per iteration, and it actually makes the number of iterations go down. It makes things faster. The quadratic shape, again, is the best possible shape from an optimization perspective, and the L2 shape of the L2 regularizer is quadratic. So L2 regularization makes things faster. Right here, one last picture about the L2 regularization and L1 that we haven't seen yet is if we have our say one-dimensional shape on the x-axis here, this position 0. It's the L1 regularizer makes a V shape like this. That's the omega value. Omega of W for L1 makes a V shape. And right. That's the omega of W for L2. And so it's a rounder shape. So it's supposed to be a parabola right here. Has a rounder shape, easier to optimize. Vast majority of times when people apply L2 regularization, it's for statistical reasons, to adjust the shape or adjust our in-sample error versus generalization error, change our overfitting, but occasionally used to make the optimization a little bit easier and faster. The elastic net regularization, that was just the mixture of L1 and L2 regularization. So the mixture, elastic net mixture of L1 and L2 regularization. And so it's going to, the hope of elastic net is to get the best of both worlds. It'll still have the same overall effect on the in-sample error, generalization error, and out-of-sample error. It does make the number of non-zeros go down because it has the L1 component inside of it. With that same asterisk, you can use it for smaller VC dimension. Yeah, to reduce your VC dimension to get that k-sparse pass basis. The time per iteration is the same, but the number of iterations is only a little bit larger now instead of a lot larger like it was with the L1 regularization. The elastic net regularization again looks like it's going to be somewhere in between these regularizations, and it's a mixture of these. Yeah, orange line right there is the omega for elastic net. And you use elastic net if, again, you need sparsity from L1. But the computational speed of L1 is too slow, and so you want a little bit faster with L2. Any questions on this or the table just above this.
Yeah, why doesn't, L2 have an effect on the sparsity or?
Question is, why does L2 not affect the sparsity? The answer is, if we were to draw out these sorts of, same sort of picture here, where instead of having this, like points, L1, the key thing about L1 regularization is that it comes to particular points here, and the in-sample loss curve here, these contour lines are more likely to strike at a point than they are to strike at the face over here. But the L2 curve is not going to have any points, and so it will always have some effect of the W2 and the W1 values. Getting into the Y of the L2 versus L1 causing sparsity, that's could easily be a course all in itself of just talking about the mathematical properties of those two regularizers and situations where why it's causing sparsity, or is there proofs it's going to be sparse or not sparse, things like that. But the main intuition to take away is L1 is pointy, so it's going to intersect these loss curves at the point more likely than at the surface, at the straight line. And so because of that, it is going to induce sparsity. L2 does not have that property. And in fact, L2 regularization never induces that sparsity.
Sorry, you mentioned this, but you're saying the last event is kind of like L1, L2.
Yep.
Does L2 come from, or I guess like, it's obviously the number of non-zeros in the BC dimension is kind of coming from L1, is the number of iterations. I guess where like.
Exactly. So on the one way to think about the elastic net over here is that this part is from the that's from the L1, and this part over here is a mixture of L1 and L2. That's sort of like this one down arrow here is canceling out some of the up arrows over here. So it's usually still a little bit slower than no regularization, but it's not nearly as slow as the L1. So this is from the L1 and that combined version. The remainder of this notes packet here has some problems that we'll start working through. They get into the why we care, when to use these techniques, how to recognize what to do with your regularizer. So problem number one over here, and again, these are going to be similar to the sorts of things that you'll have to do on your final exam. The information up here is more background to get you comfortable with understanding why the problems down here are the way they are. So problem one, you're training a logistic regression model within training data points of dimension B, and you expect the optimal value of C and lambda to be large or small in the following circumstances. So here, if we have N is greater than D, then this is, we can't exactly say whether we're overfitting or underfitting just from this information. So we're more in the underfitting range. So I'll say compared to part two down here, where it's more in the overfitting range, this is more in the underfitting range. Doesn't mean we're guaranteed to be underfitting, doesn't mean we're guaranteed to be overfitting down below, but this is more underfitting, more overfitting. And so if we have all of these data points, then we expect we don't need a lot of regularization in our problem. And so our C value will be large, or equivalently lambda small. If both of these, either of these imply little regularization. And this is usually the realm that we want to be in. Again, if we have that rule of thumb of 10 times the VC dimension is the number of data points, then with n greater than d, we're pretty close to this rule. We're about in this range that we expect good things to happen. Don't need a lot of regularization. But if n is less than d, then we're almost certainly going to be in the overfitting range. Probably able to shatter this data set with a linear classifier here, logistic regression. And so we need to control the capacity of our model somehow. And let me follow the thing from my head. So C will be small, or lambda large equivalently, because they're equal to the reciprocals of each other. And so those are equivalent to saying lots of regularization. So previously, the only tool we had to, if we were overfitting or underfitting, was changing our VC dimension, changing our hypothesis class, or changing our feature map. But now we have this new tool that's also somewhat related to optimization, that we can change how much regularization we have, and that will also adjust our overfitting or underfitting. Any questions on this problem? Yes.
It's like that, or like, you drop it and all that, but it's like over to the communities person about like why and is more understanding, like I'm thinking that it's like you don't have enough dimensions to like represent the data, but that would just like explicitly state why it's like or something.
Yeah, let's see. So that's a good question about like here I wrote more overfitting and more underfitting. Maybe let's just toss out those terms. Those are bad things to say. And even though I said it in class right now, not the sort of thing that would be good to say on the final exam. So like if your n value is greater than d, you are more likely to be underfitting compared to this situation down here, n value less than d. As your n value increases, when you have more and more data, you are less and less likely to be overfitting, more and more likely to be underfitting. And I'll say that there's no need for constraints on the model. Again, if our n value is greater than d, then we're could possibly be in this approximate sweet spot over here. We don't know whether we're overfitting or underfitting. We just know that we're doing better on the overfitting, underfitting side than if we have less data points than dimensions. Because if we have less data points than dimensions for logistic regression, if we do in fact have no regularization going on, this would in fact imply that our in-sample error En equals 0 for no regularization. Because without the regularization, we are just directly minimizing the in-sample risk, and the perceptron is able to shatter any data set of size D. And so we're definitely able to shatter this data set right here. So this would be a definitely overfitting scenario. the only option that we previously knew about how to solve this situation, how to resolve this situation, was to reduce our VC dimension somehow so that we had more data points than the VC dimension. But it turns out that's not the only thing that you can do. We can make it so that you're not actually finding the empirical risk minimizer, and by constraining your hypothesis class with these regularizers, that will possibly take you out of the overfitting scenario. So I guess the important part here is that this part two, it's this because we have fewer data points down here in part two. That's what's causing our C and our lambda needing to be how they are. So n being smaller, n going down is what implied with the C should also go down. I don't know if that was sort of answering. Good. Yeah, so the important thing here, again, what I was hoping that you all would take away from this is the difference between part one and part two here is that in part two, n is smaller than part one. And because n is smaller, then our C value also needs to be smaller. Because n is smaller, we are more likely to be overfitting. We're more in the overfitting direction. And so we can counterbalance that by making our regularization smaller, C value smaller, or our lambda value larger. Problem two here's a little bit more maybe concrete. So here, your training logistic regression model within training data points of dimension D using stochastic gradient descent. How will the optimal values of C and lambda change, increase, decrease, or stay the same in the following circumstances? So you double the number of data points in the training set. So if our n value increases, that pushes us into the underfitting direction. We're not necessarily underfitting. It's like the derivative of underfitting increases. If n value increases, we're more in the underfitting direction. That our in sample error is going to stay the same or increase, but our generalization error in minus E out, that's going down because that is equal to the O of square root dVC over N, and we reduce the denominator here. And so in order to, if this value is going down and our in-sample errors either staying the same or going up, then in order to counterbalance this, we need to make our model more complex somehow. And again, we could do that by trying to adjust our VC dimension somehow, but the regularization gives us this new tool to be able to make our model more complex, and we can do that by making our C value increase, which is equivalent to making our lambda value go down. So the reasoning about these C and lambda values is the same sort of reasoning that we were doing previously on our VC dimension, that if we are in the overfitting side, we need a less complex model, and we can adjust that with C and lambda, or vice versa. In this case, if we're in the underfitting side, we can make the model more complex by making our C value larger or our lambda value smaller. Okay, if we double the number of data points in the test set here, though, then this has no effect on our E in or our generalization error in minus E out. So the C and lambda both stay the same. In general, whatever changes you make to your test set, not going to have effects on the decisions you make about optimizing the balance between the in-sample layer and the generalization layer. We're through right here, so the third degree polynomial, so the VC dimension is going to go up a lot from applying the third degree polynomial. So again, the model complexity has increased a lot. If we were perfectly balanced on our model complexity before applying the third degree polynomial, then we are now going to be overfitting, and we need to bring our model complexity back down. Bring complexity down, and we can do that by making C smaller or lambda larger. So if somehow we've made our VC dimension bigger, we can counteract that effect with our regularization terms. Number 4 over here. So we applied the PCA kernel. So this is just the opposite situation. We've made the DVC go down, and so that's going to mean in order to keep the model complexity somehow the same, we'll be doing the opposite of up above. All this reasoning will be the opposite. The DVC down, so our model complexity has gone down. So we need to increase the model complexity. Need to increase the complexity. And so that means we need to make our C value up or lambda down. It's the opposite directions that we had over here. DVC going up means that to counterbalance that effect, C down or lambda up. And DVC down needs to counterbalance C going up or lambda going up. Number 5 over here about changing the optimization algorithm doesn't affect the statistics at all. Doesn't affect the E in or our E in minus E out. And so our C and lambdas can stay the same for the same model complexity. One last one here, doubling the number of dimensions. So D increases, implying the DVC will increase, and that will imply the same reasoning that we had right here, that C should go down or lambda up. Any questions about any of those? Yeah. One last problem on this notes packet, which I will leave for you all. This is the sort of problem that is common on interviews. We've done actually this problem optimizing ordinary least squares without a regularizer in a previous notes packet. This is adding the L2 regularizer and seeing that it still has a closed form solution. So ordinary least squares with this L2 regularizer here called ridge regression commonly, and it still has a closed form solution. So this will be a problem that we won't do in class, but good for you all to do on your own. Okay. Last few minutes of class today, we're gonna start talking about this model zoo set of notes and give us some sense of direction for the last month or so of class here. So far what we've done, we've talked about a handful of tools that we have for adjusting the in-sample error versus the generalization error of our models. And we've tried to motivate why that's the case, because it allows us to minimize the out-of-sample error by cleverly adjusting these things. One of the weaknesses of the textbook is that they limit their discussion to just linear models and then making them more complex with the polynomial kernel. But there are many, many other models that people do care about in practice. And so this set of notes, this next topic is going to cover a lot of those models that people care about in practice. There's everything from these sets of notes will not be in the textbook at all. Instead, I'll have other references either to the scikit-learn documentation. We're mostly going to be following after this set of notes, we will have covered every model implemented by the scikit-learn library. So the other references will come from their documentation, or it'll come from other textbooks or papers where I will just pull out like a VC dimension formula, but you're not responsible for going through and reading those other documentation. Yeah, so this part 2 right here, this picture of models, this shows a handful of different decision boundaries. So one way of visualizing all of these models. We're going to be talking about all of these statistical properties of all of these different models to help us understand why you want to use one model in one situation and a different model in a different situation. The first thing that we'll talk about is really easy, this 2.1 here with linear and quadratic models. So it says, recall that a model refers to both a hypothesis class and a training algorithm. And we've only covered one training algorithm or one class of training algorithms, of gradient-based training algorithms. But this training algorithm right here, something like 1GD or 2GD or SGD, are examples of training algorithms. But there are many other types of training algorithms, and it turns out that they're not used anymore in practice. They're strictly worse than these first gradient descent, second gradient descent SGD algorithms. So the scikit-learn implements a handful of these linear classifiers and quadratic classifiers. And the first important difference about them is which ones use worse optimization algorithms than gradient descent family, and not to use those. So that's this linear discriminant analysis, the passive aggressive right here, and both of these, all four of these, the things in blue, they don't actually directly minimize in-sample error. Oops. These don't minimize E sub n. They do something else to select their hypothesis. And so almost always worse. Almost always worse than, say, the logistic regression or support vector machines. The other models here, so we've seen the perceptron with the perceptron learning algorithm. You can squint the right way. That's an example of stochastic gradient descent. This is also one that's not used in practice anymore. Not used in practice because, again, actually optimizing the 0-1 loss is NP hard, and so you'll be waiting an exponential amount of time if you use your perceptron. The logistic regression right here, this is implemented with 2GD, and the SGD classifier down here, this is implemented with 1 SGD. And so you choose which one of those two to use, logistic regression or SGD classifier, based on which regime you're in, whether you're in the large scale regime where you are limited computationally, in which case you use the SGD classifier. But if you do not If you are not limited computationally, then you use the logistic regression model, which uses that two gradient descent implementation. The linear SVC down here also uses two gradient descent. This just uses the hinge loss instead of the log loss. So whether you were to use the linear SVC or logistic regression is sort of a matter of preference, but they're basically the same. So basically same as logistic regression. The difference is that it uses the hinge loss instead of the logistic loss. SGD classifier lets you actually specify which loss you're using. So SGD classifier is the SGD version of both of these two implementations here. Last important thing to mention here is so the VC dimensions of these hypotheses classes, the linear classifiers over here, the VC dimensions are all linear. DVC equals G plus 1 over theta D for all the linear hypothesis classes, and then in the quadratic classes, the DVC over here is always theta of D squared. I'll scroll down in a second. There's a list of all the different options to the logistic regression and SGD classifier and linear SVC down below. You're responsible for understanding all of these options and how they affect the classifiers, but these are all things that we have talked about previously, just potentially in different language. So here, this C is the actual same C value in the previous set of notes. The penalty over here is equivalent to the omega function. You have to decide is it the L1 or L2 or elastic. The tolerance here, this is when we decide to stop doing our optimization. So this only affects the optimization error. When we decide to stop doing our optimization, how many iterations are we going to do? The fitting the intercept is, do we add the bias term or not? So if true, that implies the VC dimension increased by 1 equals D plus 1. False implies the VC dimension still remains equal to exactly D. Basically, everybody always sets that to true. And the intercept scaling is whether you want to actually learn that parameter or not. Max iterations, how many times you're going to run your optimization algorithm. So that also only affects EOPT, nothing statistical. L1 ratio is this if you're using the elastic net. This is the alpha value from elastic net. So all of these things are things that we have talked about in potentially slightly different language, but things that you should be able to think through about how to adjust their parameters in order to improve performance. And in the next couple of classes, we'll be seeing a lot more examples of these classifiers talking about their different hyperparameters here that we can select and how you might want to select them based on the information we've seen so far. It's a good stopping point for us for today, so stick around and answer any questions that people have. Otherwise, it is the end of class.
Yeah. Like.